Hello, class. Welcome to today's lesson. So this is for machine learning, CSCI 221, and today's class is all about dimensionality reduction. Okay, and in this instance, the method that's going to be used for dimensionality reduction is called PCA, which is short for principal component analysis. So I want to give you an explanation of what that is, and then I'm going to show you how it's implemented using Python. And then at our next class, we'll be implementing it using R. Okay, so, and I will be glancing occasionally from side to side to refer to my notes as I normally do in class. What is PCA? So principal component analysis, what that does is that it allows us to work with a data set and decide to reduce the number of variables to a specific number and then use those variables to create models. And the reason we may want to do that is because sometimes data sets just have way too many variables, right? And sometimes it makes it difficult to select which variables would be the best for your model. As you've already experienced when you were selecting variables, when you were implementing multilinear regression, right? Where you had to select variables, and some of you mentioned that you chose variables for specific reasons, mostly because how they influence the target variable and whether or not they increased or decreased the accuracy of the model, of the prediction model. And so with principal component analysis, there are methods included in some of the Python libraries that allow you to reduce the number of columns in the data set while still maintaining a lot of the information that's necessary to make that data still reliable, even with removing those variables. Now, one thing to keep in mind about principal component analysis, actually, there's two things to keep in mind. One thing is that this is done after you clean the data, okay? Because in most cases, most of the methods for principal component analysis, whether it's in Python or in R, will not function correctly if there is missing data, if there is duplicate data, or if there are outliers. So now you can see how all the things you've been learning so far are going to be now included and be cumulative for the models that you're going to be creating going forward and improving the models that maybe you already created. All right. But you do have to perform your data cleaning before implementing PCA methods. The second thing to keep in mind about PCA is that the components or the variables that it creates, it's not a rehashing of the variables that are already there. What it in fact does is create new variables. You'll be able to visualize them as I'll show you in the example, but these are new variables that you're creating. You're not rehashing the ones that already exist. So keep that in mind as well when you're considering what kind of data is producing when you visualize it after implementing the PCA and just deciding whether or not the accuracy of your models using PCAs, whether or not it's effective and whether or not it's worth doing PCAs by removing the variables or not. Okay, so just keep those two things in mind. And what I'm going to do now is I'm going to switch to the code editor. I may switch back and forth, but mostly be on the code editor, Visual Studio Code, so you can just see what it's done and what is done and how it's done. Okay, so I'm just going to switch there now. Okay, so here we have a Python notebook, and we have the standard steps here when we're importing the libraries that are necessary. And so for PCA, what you're going to be importing from the sklearn library, besides the data sets that you normally do, is the pre-processing library, because we're going to be using that to scale some of the data, and then the decomposition library, which includes the methods for principal component analysis, as you see here. So these will need to be included. And I will be providing this sample code to you as well to use in practice, as well as for you to modify for your assignments that are due this week. Okay, so for this example, we're going to be loading the built-in iris data set. And so it's always a good idea to preview data sets before you implement PCA because you want to know what you're working with, right? So in this example, we see that the iris data set has 4 columns and they're all numeric. Okay, so that's one good thing to know, because when you're deciding to make changes to your data set, you want to know what you're starting with to give you an idea of what you may want to reduce it to, because that's what PCA is all about. It's all about reducing the number of variables to make data analysis and potentially manipulation simpler and easier to understand. Okay, so like I mentioned before you can implement any principal component analysis, you're going to need to clean the data. So as you see here, I've taken the steps to account for any missing data values, any duplicate data, and also I decided to check for outliers by using z-scores. Okay, as you can see here, there was no missing data. There was one duplicate row and there was one outlier. And so since they were so small a number, I decided to remove them instead of imputing any values for the duplicates. And for the outliers, there was one, it was removed. Okay, so we can see now that the data set is down to 148 observations. Okay, so now is when we start the process of standardizing the data. And one other thing I do want to mention is that PCA is like the final step of cleaning your data. Okay, it is the final step, because once you do PCA, you can then choose to use these variables to implement models. For example, you could use PCA data to implement something like a k-means clustering model. Okay, so just keep that in mind, that this is creating variables to be used in models, and those models should yield better results using these new and reduced variables. Okay, so let's get back to the code editor. All right, so after cleaning those first steps of cleaning the data, we're going to standardize the data using the standard scalar method. Okay, and then we're going to fit that data to the scalar. Okay, so we have the variable here holding the scaled values, and then we're going to apply the principal component analysis. So for right now, and there are other methods to try to decide a better number for principal component analysis, but for right now, we're going to select the number 2 for principal components that we want to reduce to. And the reason that we want to do that is because typically when we're visualizing these results, having 2 variables makes it much easier to chart. Now, Python does have methods for charting, for creating charts for data sets of more than 2 variables, right? We can create 3D charts. We haven't gotten to that yet. But for this lesson, for this week, we're going to stick to using 2 components, or reducing our data set to 2 variables, so that we can be able to graph it later and be able to visualize it and understand what's going on with that graph. All right, so we're going to apply the principal component analysis method by giving the n components attribute a value of 2, right? That's what we're going to reduce it to, and it's going to transform the data to generate those principal components. Okay, and then the way that we're going to evaluate this principal component analysis is by a value called the explained variance ratio. Okay, and what the variance is the amount of data that the spread of the data, meaning how far apart the data points can be. Okay, and so then when we talk about the explained variance of the data, what that's doing is it's telling us how much of the original data's total information is captured by each principal component. Okay, so since we do indicate that we want to reduce it to 2, there's going to be 2 principal components. They're going to be labeled PC1 and PC2. But this explained variance ratio will tell us how much data of the total data set is retained by each of these components. All right, and so the way you evaluate it is, first of all, this number is going to be multiplied by 100, so you can get an idea of what the percentage is. But typically, the total amount of the percentage of your principal components is going to let you know just overall how much of the data was retained. And the closer to 100 of the percentage that you have, the better that it is. So you can see just from this example, when we look at how what the ratio is for the first component and the second component, right? We can see that approximately the percentage approximately retained data for the first component is about 72.9%. And for the second component, the approximate amount of retained data is 22.8%. So that gives us a total of 95.7% of the information that was kept, even when the data set was reduced to 2 variables. So we can feel confident after reducing this data set to 2 variables that most of the data is retained and that any models, generated from these principal components can be deemed to be reliable. So this is the evaluation metric that we use when considering principal components. Okay. And then finally, after we get that ratio, we can also visualize the components. Okay, so we can indicate which component is going to go on the x-axis and the y-axis. Of course, we can give it the chart a name. And then what we see here is a scatter plot. Okay, so what does this scatter plot tell us? Okay, so when we're looking at the scatter plot, it tells us a few things. One, you should understand that each point on the scatter plot, each point represents one observation of the data set or one row in the data set. All right. The other thing you should understand is that each position of the dot, it indicates its value in these new principal components. Okay. So that's what the position means. Now, the distance between the points is also something to consider when looking at this chart, right? So when points are close together, for instance, when we see this group of purple points, the blue ones or the yellow ones, those means that those points are similar observations. And then points that are far apart, of course, they are different. So what we can see just by looking at this graph or this data set, we can see that those items that are purple are similar, but they're definitely far apart from those that are blue and yellow, whereas the blue and yellow ones may be considered similar observations. Okay, so this kind of chart is useful because it helps us now to get a better idea of how this data may work out if we decide to implement clustering or if we just want to start looking for any patterns that exist in the data. Okay, so when you see these points, color coded and displayed in this way, another thing to consider about the way they're grouped in the graph is that some groups, when when they're clearly set apart, for instance, like these purple points, that means that the data, the component that those belong to generally tend to be strong in structure. They're very close together, not a lot of variance. Whereas where you have overlapping groups, like these blue and yellow observations over here, tends to mean there's weak separation of the data. Okay. And so generally speaking, if you were to cluster this data, you would probably get 3 clusters to categorize the observations in this data set. Okay. When you have a wider spread along the PC1, meaning the principal component number 1, it tends to mean that a higher variance was captured. Okay. And again, what we mean by variance is the spread of the data. So even though there is a big spread of the data, and again, we can see that from the distance between these dots on here, between the purple and the yellow, that tend to be the 2 ends of the data set, it's this principal component analysis did allow us to create these new variables that captured most of that variance. If these had been closer together, for example, the way we see the blue and yellow dots, that means that less of the variance was captured between these clusters. Okay. So this is what we're working with when we're doing principal component analysis. We are reducing the variables, and then we're creating new variables and then graphing that to give us an idea of how this data is spread, whether or not it's going to be reliable to use when we create our models. Okay. So I just wanted to give you that lesson for today since we were not able to meet, unfortunately, in person, but I am looking forward to seeing all of you on Thursday. I did post a practice exercise. I will double check to make sure that's live. If it's not, I will make it live now. And I would like you to um, try that practice exercise until we meet in class on Monday, and just post your replies to the discussion to see what you get as far as practicing the dimensionality reduction with Python. And then we will get further into more details with understanding the visualization of the data and other items that are best explained in person. And we'll also be doing PCA using the R programming language. So let me know if you have any questions. Otherwise, have fun with the practice. Make sure you do the readings in the Python book as well as the Geeks for Geeks article that I shared. Also, I did update the readings to include information on how to access built-in data sets with Python and R, because you will need that for future assignments. So it's good you just know how to do that now. And I will see you all on Thursday. Thank you very much, and you have a good night.